So we're now going to move on to the first of two applications I mentioned in the very first video with regards to algebraic identities. And the first one we're going to be doing is this thing called partial fraction decomposition. Now, I will point this out, this is not something that has to be memorized. The questions, particularly in textbooks that I've seen, will always give you what the corresponding decomposition is, and will ask you to write it in whatever form that is, whatever form they want kind of on the day. But I will just go through one example where I will state the rough form of these sort of partial fraction decompositions. And before I do so, it might seem very odd. This seems like a very pure thing to do, but I will say that, particularly in a lot of computer simulations, it's easier to do an addition of two fractions instead of trying to get everything done in the same fraction. At least from the stuff that I've tested in my very sort of bare bones attempts at Python. So, in this particular example, we have the fraction 4x take away 5 over 2x minus 1 times x minus 2. And the question might say to write it as two separate fractions in such and such form, or they'll ask you just to have it as an identity question. And the form that this particular partial fraction will go into is a constant a divided by the first bracket, which is 2x minus 1, plus another constant b over the second bracket on the bottom, which is x minus 2. So we're effectively like pulling apart these as separate fractions. And these a and b's are simply constants for a reason I kind of won't get onto it initially immediately. So there's two ways of doing this. This is the way that I often teach this very sort of small bit of algebraic identities. What I'm going to do is I'm going to multiply across by the denominator because I really don't want that there. So multiply across by the quantity 2x minus 1 times x minus 2. What we get on the left-hand side is just the top, so the 4x take away 5. And we want that to be identically equal to a times, well, when we multiply across by this, the 2x minus 1 here and here are going to knock each other out, leaving us with an x minus 2, plus b, multiplied by, when we multiply across by this denominator again, the x minus 2's are going to knock each other out and will leave us with a 2x minus 1. Okay, great. Couple of ways we can do this. We can substitute in completely arbitrary values, like we might pick 3 and 4, just because that will give us nice numbers. But there's a quicker way of doing this. Firstly, if we let x equal to 2, this bracket is going to completely disappear and we're just left with a linear equation in terms of b. So 4 lots of 2 is 8, take away 5 is 3, is identically equal to 2 by 2 is 4, subtract 1 is 3b. So we get big B is 1. And similarly, if x equals to a half, completely knocking this bracket out, 4 times a half is 2, subtract 5 is negative 3, is identically equal to a times a half, so that's minus 3 over 2. I hope. 4 times a half is 2, subtract 5 is 3. A half, subtract 4 halves gives us minus 3 halves. So 3 is identically 3a over 2. So a is 2. So great, we have our values of a and b. So we can declare that the fraction 4x take away 5 divided by 2x minus 1 times x minus 2 is always the same as a, which is 2 over 2x minus 1 plus 1 over x minus 2 for whatever values of x that we want, provided that it's not a half or 2 in this formulation. So I'll point out that the partial fraction decomposition is not always as easy. There's definitely a lot of more complex variations, especially if you have, say, if there's a 2x minus 1 squared, the form be a little bit different. If there's a quadratic factor in the denominator, things get a lot trickier. However, we're just going to stick with simple linear equations and linear denominators. Well, linear factors in the denominators. Just so we can get these fairly nice forms.